Coulomb's law for one dimension at a time, using the formula negative k, the first charge qa, the second charge qb, all over r squared. However, at this point, this is only useful for so much, right? If you have two charges, of course, we're going to call this here charge A, and then let's say over here you have charge B. Of course, this formula is going to work great for that, to show the forces that are acting on both of these. However, as soon as we add in another force, or another charge, for example, what about right here? We'll call this charge C. This becomes much more complicated than it was before, because in fact, let's sort of give these some values, and then let's sort of think about how these would move. So if this was here, if we made this 3 coulombs, and this here 4 coulombs, and then this negative 2 coulombs, we're going to see two things happening at this time. We're going to see, so what's important to note here is we're not going to see how all of them are moving, rather, we're just going to see the forces that are going to be applied at this exact moment. So that's what this formula is actually really calculating, because if you think about it, if these forces caused these charges to move, it would thus also affect this r squared value, which would be recursively affecting how fast they would move. So that's why this is called electrostatics. We're just looking at this, a snapshot in time, looking at the forces that are going to be acting on this. So if we see this is a negative force, and so then between these two, we're going to see attraction between them. So here, we're going to see that A is going to have some feeling to attract this way, and B is also going to feel a force to attract that way. However, just because these two are attracting doesn't mean that nothing's happening between A and C here. A and C are, if we remove B, the equation still applies to A and C. We just see that this is Q of A and then this is Q of C. And we're going to see that due to this, they're going to move away because these are both positive charges. So I'll sort of draw the force direction vector of these two. And of course, since the distance between this and the distance between A and B, or the distance between A and C is bigger than the distance between A and B, we'd likely see a sort of smaller force. However, we also have to take into account that this 3 and this 4 has larger magnitude, larger absolute value essentially than this. So it's going to be sort of a mix between those two to see how big these vectors are. And obviously we can calculate them, and we'll do that in a second. And so we've looked at how A and B are interacting, how A and C are interacting, but B and C are also interacting as well. If we do this in a different color, we're going to see that this is negative, this is positive. We're going to have some attraction between these two charges here. So this is going to want to go downwards, this is going to want to go down upwards. And so, like we've learned from the property of superposition, which you might remember from AP Physics C Mechanics, superposition is this idea that a single charge can be affected by the multiple charges around it, and the vectors of force that are caused by the charges around it can be added to get a total understanding of the charge of the entire, or not the charge, sorry, the force of the entire charge. And so we saw this with gravity. With gravity, we saw that if we had multiple different masses all floating around in space, that we'd have to look at each of them and the interactions between them to see how one of them moves. So if we just apply this property of superposition to this value b, we see that we would take this vector that's attracting it this way, and we'd take this vector that's attracting it downwards, and we'd add them together, and we'd get a resultant vector that looks like that. So based on, at this moment, if we took this snapshot in time, we were looking at this, we'd see that there'd be a force vector on B causing it to move in this direction. And that makes sense. Both of these, if we sort of think about it, are both pulling it this way and this way. So it makes perfect sense that they would come. Okay, so then how can we actually calculate that? Let's pull out some math and see if we can use superposition to calculate the exact force that we would see on B. So when we do this, we are considering this as a vector, right? And so the most important thing to start with is to define an origin. And so in this case, we should define this origin. Or I think the best origin, we can really choose any spot here, but I think the best origin is right on B, because that's what we're trying to figure out. So we'll call this is sort of our 0, 0. 0, 0. And then if we were told that there was a distance of 1 meter between B and C, then this would put C at a position of 0, -1, because it's in the y direction, 1 meter down. And then this puts A, imagine if A is also 1 meter away. Actually, you know what, this looks like 1 meter, maybe this is 2 meters. So this will have -2, 0 in the y direction. So we've defined our axes, and so now it's just a matter of finding the x force vectors and finding the y force vectors and then adding them together to get the total force on B, because that's what we're trying to find. So let's write that up here. Total force on B. Force on B. And we can give our answer in terms of K, because I think that'll be easier. So the total force on B, let's find that. So in the x direction, sometimes I just like to split it up like this. In the x direction, we have a negative force. We're saying that this is negative, right? And this is also negative, right? Just like how you would see on a Cartesian coordinate axis, just like you've done in mechanics. There's going to be a negative force that's between these two items. And so we're going to say -K. We have our 3 coulombs here, 3 coulombs times we have another 2 coulombs here. And you'll notice that I'm not really accounting for the fact that this is -2 coulombs and this is +3 coulombs, because we've already logicked that out and figured out that we need to put this negative up here. So rather than having the math take care of that for us, like we could have done, we're just sort of thinking about this ourselves and figuring out if it should be negative or positive. So we have this negative force vector, and so then this is 2 meters. This is going to be 4 meters squared on the bottom. So this is an expression for the force in the x direction on B. So let me actually write that using actual good notation. So we'll say the force on B in the x direction is that. Now the force on B in the y direction is going to be solely based on C. And C is going to be pulling it downwards. So we'll also call that a negative force. And so then this is going to be 2 coulombs. And then we're going to have this 4 coulombs. And between them, we have only 1 meter. So 1 meter squared goes on the bottom based on our equation. And so with this, we can get that we're going to have 6 over 4, negative 6 over 4k, right? So that puts us at negative 3 over 2 k newtons of force in the x direction. And then we're going to have 8 over 1, so negative 8k newtons in the y direction. And generally, if you had a calculator with you and you were doing this on a test or homework, you would plug in k as 8.99 times 10 to the 9th, or just 9 times 10 to the 9th. However, just for simplicity, I'm going to do it this way. And so now, with all of this, we've utilized this property of superposition to figure out the exact forces that are going to be acting on B in each direction. And so we can write that down. The force on B is going to be the vector negative 3 over 2k, and then negative 8 k in the y direction. Okay, so then if we want to figure out the exact direction this is moving, we could calculate these numbers out, of course, plugging in this k constant, and we could use tangent inverse, of course, just basic vector properties to figure out the exact direction, and then we can also figure out the net, this should be a vector really, we can also figure out the net force that's going to be acting on that just by finding the magnitude of this vector. So f of b, or sometimes written like this, the magnitude of vector b, and that will essentially give us the amount of newtons in this direction which is moving, right? So that's going to be 3 over 2k, which is going to be 9 over 4 k squared, because we're squaring this, k squared. And then if we square the top and bottom of this, we're getting 64k squared. And if we take the square root of this, I should have used the other color here. But if we take the square root of this, we'll find that this is the exact force that's acting on B in this direction, and this is the direction that B is going to be moving. Okay, so before I leave you, this is essentially the entire property of superposition that you need to know. Let's sort of imagine just one more thing. And we're not going to solve this all the way through, but it's just something to consider. If you also added another charge onto this, let's say we call this charge D, and this D will put at the position 1, 0, and D had a Coulomb rating, or charge is the better word for it, of negative 13 coulombs. Let's just sort of think about how B would be affected, because B is our sort of main character of what we're trying to find, the total force on B. So in this case, B, this negative and this negative would cause these two items to repel from each other. So that would result in a net force vector on D going this way, and another net force vector on B also going this way again. And so this would only add on to this this term here. We'd add on another one of these, right, for D, plugging in 13 coulombs, 2 coulombs, and this distance of 1 meter. And then we'd get a larger value for X because of this larger push to go this way. So that's something to consider, and it's something that we didn't see as much with gravity. We never saw gravity sort of pushing things away, but in charges, if you drop a random charge here and it's of the right magnitude and right sort of polarity of charge, it can sort of push things away just as much as it can move things closer to it. So with all of that in mind, that's the property of superposition, and that's how you calculate forces on charges in 2 dimensions. And of course, extending this to 3 dimensions is most likely not something that you're going to have to do. However, you would just extend this math as well to include a last 3rd dimension, just like you did with gravity.